Let's now solve some problems with importance sampling. Here is the algorithm that you see on your screen. We have to identify the basic variables of the problem, which we have been doing regularly the last few lectures. And then we have to know the joint density function of these basic variables and be able to define the failure criterion, the limit state equation or equations. When we say equations in the plural, we mean there is a system level problem defined. This algorithm is going to work equally well for systems, but for now our focus is component reliability of the capacity demand type. So we are able to define the limit state, and then in importance sampling, which was not necessary in basic Monte Carlo simulations, is we have to identify or at least get an idea of the most probable failure regions, maybe again in plural, in the basic variable space, because that's where ultimately we want to do most of the simulation. And then to do that, once we know the most probable failure region, we have to propose an importance sampling density function. This density function we have been calling FV, and if there is a dependent structure in Fx, FV may or may not have any dependent structure. Both are fine. If we want to have a dependent structure in FV as well, then it may follow the same as that of Fx. And now once we are ready with these preliminaries, we will start the simulation. We will generate the basic variables from the importance sampling distribution FV. So it is the shifted, the biased distribution, and then with that x that we have sampled from FV, we evaluate the density function FV there, we evaluate the density function Fx there, the same point, and then we evaluate if failure has occurred or not, and if failure has occurred, then we store the entire quantity that we are taking the expectation of. If you remember our basic setup, that is Fx over Fv, that ratio of the two density functions, and I obviously is 1 if failure has occurred. So we keep doing this until we are done with the simulations, and whether we have reached convergence, our uncertainty in the estimate is below our tolerance levels. We keep doing that, and then once we are happy, we come out of the loop and we estimate the PF and the associated uncertainties and report those. So this is the algorithm that we are going to follow, and the first example we take up is the one involving again our old friend, the cable in tension. It's the example group D1, which has 4 random variables, and let's just take a few seconds to read through the problem, and then we will go through the steps in solving it. Okay, so the nature of y, a, q, and d, they're the same as before. There is a correlation coefficient between d and q. We have to employ an ATAF transformation for them, and we can use the most probable point found from form that we have already solved. And there we are going to locate the importance sampling density function. Okay, so this is our limit state. It's x1, x2 minus x3 minus x4. We have seen this several times already. And then the individual random variables are distributed as you see, fy, fa, fq, and fd for x1, x2, x3, and x4 respectively. The basic variable joint density function fx, that is based on the information given. It's the marginal density of y times the marginal density of a times the joint density of q and d. And these are evaluated at x1, x2, and x3, x4 respectively. The importance sampling scheme is, we just, for completeness, we list it here. The failure probability is estimated as the expectation of I fx over fv. And these x's are generated from the density function fv. And that's what we do repeatedly, as I described in that flowchart, that the PF estimate is the average of the importance sampling multiplied by the density of the multiplied by the ratio of the two densities. Okay, so we now have to have a scheme of generating these 4 random variables from their importance sampling density. For x1 and x2, for yield and area, it's straightforward because they are independent. All we need is to be able to know their marginal distribution function, and we can invert that with a uniform 0, 1 deviate. For Q and D, we need to go through a few steps, so let us take them. The joint density function of Q and D is not really defined. All we know is that they are dependent, and we have been given their correlation coefficient rho. And we would like to, we have done this before, we would like to map them onto a bivariate normal density with the same correlation coefficient rho. So if that is so, we can transform QD to y3, y4, y3, y4 being the standard correlated normal bivariate. So you see on your screen the Jacobian of the transformation, and phi 2 is that bivariate normal density. So once we have the marginal, once we have the joint density function, we can obtain the marginal densities, the marginal distributions, and the marginals are recovered from the CDF to CDF transformation. Now, how do we get the density of Q and the density of D in terms of the marginal densities of y3 and y4, which are standard normal? So we can use the chain rule of differentiation, and partial y3 with respect to x3 is the ratio of the two densities, likewise for y4 and x4. So the Jacobian we are almost ready to solve. We recognize that the off-diagonal terms are 0. So partial y3, partial x4, and partial y4, partial x3 each is 0, and that lets us write out the density function, the joint density function of Q and D in terms of the bivariate normal density function multiplied by a correction factor, which is the product of the marginal densities divided by the product of the marginal normal densities. So this is something which we are going to use when we do the importance sampling. So this is what the importance sampling looks like, the importance sampling density function looks like. We choose it to be this way. that fv has the same form as fx, and we expand it as fy times fa. They're both primed. I hope you can see the prime in the superscript. They are not specks of dust on your screen, but they are supposed to be primes. And f prime qd for the dependent random variables. So we choose these primed densities to be of the same form, same type as the unprimed. So f prime of y is the same type as f of y, but with different parameters. So the u and k of the viable distribution are potentially different. So u prime and k prime. Likewise, for the area, f prime is the same type as fa prime, the same type as fa, but with different mean and standard deviation. And same for q and d. For q and d, we would like to have the same correlation coefficient for f prime sub qd, and that tells us, again, using the same Jacobian type transformation we used for the unprimed case, is the joint density of qd in the shifted sense, the important sampling sense, is again the product of the marginal primes f prime q and f prime d over the marginal standard normals times the bivariate standard normal with the same correlation coefficient rho. Now we are almost ready to start the simulation. So this is our scheme. So we now are ready to write out the ratio fx over fv. And let's see what that looks like. So as I said, for yield and area, they're straightforward. We have to just generate u1 and invert that, generate u2 and invert that. So that is not a problem. For x3 and x4, for q and d, we have to bring in the dependence, and we find the lower Cholesky factor for R, the correlation matrix, and then with that factor C, we can write the y's, y3 and y4, in terms of the independent standard normals z3 and z4. And so this is something we are just going to do once, and then with that C, we are going to define the density functions of y3 and y4, and hence x3 and x4. So that's how we do. Y3 is a linear combination of z3 and z4. Y4 is a linear combination of z3 and z4. That's how they're dependent, and we individually transform them to get x3 and x4. Finally, we can now take care of the ratio of the two density functions, and that is, as you see on the screen, on the numerator you have fx, and on the denominator you have fv. We have expanded them in the second line, and using the Jacobians of the transformation, because we have used the same row, they cancel out, and what we are left with is the product of the individual density functions, the original individual density functions, and in the denominator the product of the shifted density functions. So that's the correction that we have to use, and if we do it repeatedly, then that's how we would sum and divide by n to get the estimate of PF. So that brings to an end the method. And now let us look at the results. We have used this the form NATAF results as we were asked. So that is our the mean of the importance sampling density is centered on that form minimum distance point, y star, a star, q star, and d star, as you see on your screen. And then for the various number of simulations, we have the estimated PF and the uncertainty thereof. And you see it's quite interesting and quite satisfying that even with 10 samples, just 10 samples, we are able to estimate the PF reasonably well. It's something like 3.3% if we remember. There's a huge uncertainty, about 45%, but we have not gone too off if we choose the density functions, the importance sampling density function that we did, and the mean of FV centered on the form design point. We are pretty good. Instead of 10, if we did 100 simulations, we would stay around the same value of the estimate, but the uncertainty comes down significantly to 13%. So if our idea is to stay around 10% uncertainty, maybe 100 or 200 simulations would be enough, which is actually quite an improvement compared to the basic Monte Carlo simulations that we also have done for this problem, and I'm going to just repeat those results here for the sake of comparison. But let's just see if we did 1,000 simulations, the uncertainty comes down to about 5%. And if we went overboard and did 10,000 simulations, the answer is like 2%. So let's see where this stands in comparison with the basic Monte Carlo simulation output. So to achieve 15% uncertainty, basic Monte Carlo would need about 1,000 simulations, but we achieved that in just 100 in importance sampling. If we wanted something like 1 or 2%, we would need 100,000 simulations, which can be achieved in something like 10,000. So there's clearly a gain of 1 order of magnitude, which could be huge when the computational demand is high. And computational demand being high is not a thing of the past. Even though the computing power that we have now is orders of magnitude higher than when such methods were first developed in the 1970s and 1980s, but the gap between the problems that we can solve and the problem that we want to solve, that almost remains constant. So the need for such variance reduction techniques is always there.